or way to the proof of RSA signature. Today would be the day that we would hopefully be able to cover the entire thing. But I think we have one last page to cover. And remember that we were talking about hash functions and how useful they are. So we ran into the idea that we could, design the hash functions from scratch, or we could just use a block cipher. And we've seen some basic ideas that we could basically use hash block ciphers over here as a sort of compression, collision-resistant compression function, and then we can use them to turn them into a hash function. So those would be an idea, and then today we would also see two different definitions of hash functions. One of them is what we call HMAC, hash message authentication code. That's what it stands for. And then this is the idea that we want to convert our hash function into a MAC. Remember that the MAC is a key function. So as an input, this function should take a key. But the challenge that we have with the hash function itself is that it doesn't accept any key, right? It just receive the message and then compute the digest of the message. So the way that people have started to utilize hash function is to sort of add key within the argument of this function. Like people, you will see that there would be different designs. They would basically concatenate the key to the beginning and to the end of the message, or many different design. One of them is what I call HMAC, takes a little bit different approach, and they define two different what I call input path and output path, and these are just some repeated beats for R times, and also the same thing in hex representation. So the idea is that they want to add key to twice in two different operations to this message by adding these two operations. They have opposite locations where their bits are 0 or 1. So the idea is when you XOR the key with this input path and output path, you kind of generate two different keys. Even though you plug in the same key, but they try to even add more ambiguity to the computation by flipping some of the bits of the key so that they can inherently generate two different keys for the computation over here. So that being understand, then we go into the design. So what they do is like they do the hash function. They basically XOR the key with the output path, and then they keep what it is, and then they concatenate it to the hash of this results, which look like the same. So this is the only time that the message come in place. So they add key, input path, they XOR them together, they concatenate them to the beginning of the message, and then they hash the entire thing. And then once they hash the entire thing, then they go ahead and concatenate the result of the previous thing, and then it look like another hash again. So they hash the hash again. So this is the idea. And a lot of time I see like a lot of the students are confused that why do we hash twice? Do we get any benefit? So in order to understand that, let me draw some small example over here that why is it beneficial to hash it twice. So the point would be if we define HMAC to be, let's say we pass the key and M and then we define it to be just the hash of m, hash of k, XOR with iPad, and then we concatenate this one with m, right? So a lot of people would say that why don't we just use this notation? Why do we have to hash it twice? The problem with that would be that we call it a sort of message extension attack. And so somebody can use this one to compute the hash of key XOR with iPad and then concatenate it with m, and then you can extend it to add something else on the message. So how is it applicable? So the idea is that suppose you use a miracle hash function. So when you use miracle hash function, of course, when you want to extend this hash function, first of all, you don't know the key. So if you knew the key, then you could actually compute the MAC for any other messages. But the problem is that the attacker doesn't have the key. So when the attacker doesn't have the key, remember that in miracle hash function, so somebody can start from V0, right? Do all the computation until you get to some block that it calls compute the F, and then you get VK plus 1. And this is the hash of, let me use a different color over here. This is going to be the hash of K XOR with iPad XOR with M, right? So now that somebody wants to run this message extension attack, so I just know that they have used the key in the beginning of this computation, which they have used. So now that I need to extend this attack, extend this hash, all I have to do is that instead of starting from V0, I start from VK plus 1, and I start to add my computation and piece of the messages until I get some I don't know, VK plus N plus 1, right? And this would be actually the result of, this is going to be the hash of MK XOR with iPad XOR with M concatenated with MPOM, right? So all I have to do is to take this hash function that we have computed already, supposing that when we say hash function, I'm free to use any hash function. And if we use the miracle hash function idea, so the only time that I need to need the key K is in the very beginning over here, when I plug in this K, the value of K. And after that, pretty much everything is depending on M. So once I get to here, so you can imagine that if I want to add another extend this message and let's say add some bits to it, I just denote it as M prime, so you can basically concatenate even longer message. So if you look at the computation, it looked like that we would just basically continue with what we have, and up to here, we already utilize our key. So from here on, I don't need to know the key, right? I just continue the computation, right? By continuing the computation, then you see that I can start to add the other bits from the M prime, and then I am able to compute the hash function for this message M concatenated with M prime at some bits, arbitrary number of bits, given that I didn't even need to have the key, right? So just we just continue the computation from VK plus 1, right? So that was the trick. So given that, I think now you know that is such a bad idea.
Wait, sorry. Sorry. Why would we have the key in the middle, and then how can we continue the computation?
So
Has that always been that way?
You're right. So the point is, hash function, remember, it doesn't take any key, right? So it takes this entire input, right, as input, right? So we just do some computation, k XOR with iPad and concatenated with m, right? So a hash function would take this entire thing as x, right? And then when you do this computation, so the hash function doesn't care about this computation over here. He sees this entire bits over here as x. So he compute the hash of x, and then you get to vk plus 1, which is the output of the hash function, right? Now we are saying that the attacker can continue the computation. So if we were to have to compute longer message over here, right? Looking into the computation that we use, for example, when you use Merkle hash function, you will see that you don't reuse the key over here. So you use these keys of bits, like bits of key, which we XORed with iPad. They are used only in the beginning of this iteration, right? And then later on, in the middle of this computation towards the end, we are basically processing the bits of the M. Of course, they have their effect because they are changing V1, V2, and so on and so forth. And V1 and V2 are like chainly connected to everything else, and those would affect the entire results. That is for sure. But what I'm saying is that after we have computed those things, we get to the end of this function that we get our output. So you can imagine that. So if we were to actually compute this hash function, you can imagine that up to here is x, right? Everything is the same. So we have computed the way that the hash function works. It allows us to do this attack. So up to here, somebody already utilized the key, and now we have the effect of key in the beginning and also the message. And once we continue with that, so the effect of the key and the previous message is already in vk plus 1. So nothing can stop us to just, instead of for computing this new hash, we don't start from v0. We start from the vk plus 1 that we have. And then we continue the computation. And then we just plug in the bits of the M. And that's look like that we were, continuing whatever we have computed from M, and suppose that some part of the M we forgot to process. So we continue with that process. And after, VK n plus 1, iteration, depending on the bits of M prime. So we are able to compute this entire hash of, let's say, I'll call it y. Just like, imagine in the beginning you plug in the y instead of x. So I hope this makes it clear that, this is the reason sometimes you see that in some other design of the hash functions, they also concatenate the key at the very end. So some other designs, let me make it clear. Other designs, they do like hash of M, hash of key. They just do one hash, but they do like this one, hash of key, and then M, and then concatenate the key again, right? Because they know that this attack is possible, so that they can just continue iteration because of the Merkle design. So the idea is that you cannot extend this one, because if you want to extend anything, you need to know the key. So as long as you don't know the key, then you are not able to use this idea of, starting from, we call it message extension attack, that you start to extend and attack this message, this hash function over here. So there are two techniques that I am aware of. One is to hash it twice, and just like what you see over here. So you hash this result, and then you add some other pad, and then you hash it again. And or you see in the other designs that they basically concatenate the key in the beginning and the end of the message. This would protect this MAC or HMAC against this sort of message extension attacks. So the idea is just like roughly that I discuss over here. Of course, you cannot, because of the padding that we add to the end of the M, you cannot basically start to extend anything that you want, any message that you want. At the end, it would become some random message that you can extend, but the idea is that this attack is possible. And so the good thing is that we are aware of this attack, and then we protect our HMACs to resist these attacks by either applying two hash functions or just concatenating key K to the beginning and the end of the message, and that would protect us. So I think if you check other HMACs on especially the protocols that are used widely on the internet, you will end up by seeing some design like this one. So now you know the reason why we should do this. Another idea of making HMAC is just why not be using block cipher. So the block ciphers are also quite good ones. So we start to process the message, and then every 120 bit of the message, we generate the corresponding ciphertext. So we would follow the same thing. We start, for example, here we are talking about the CBC MAC. So we are using the CBC mode of operation. So we start with some initial IV, and then before we encrypt the message, we XOR it with the previous block of ciphertext, and then we XOR it with the message I, and then we encrypt it to create a new block, ciphertext block. And then we continue. And then the idea is that after we did all the computation, we would drop everything, and then we just stick to the latest block. So if you remember the design for the CBC, so we have done a lot of computation over here, right? So this is the IV, and then the message comes in, we XOR it with the IV, maybe M0, and then we compute the C0, and then this goes and encrypted and XOR with M2, M1, and then we get the C1 and so on and so forth. So the idea is that at the end we receive the CL. It is the latest block. So we are going to define our hash function. So the CBC MAC for this message with this key, we are going to define it to be the CL, right? The only latest block over here. And then we're going to ignore the previous ones. It is fine because the purpose of the hash function is not to recover the message itself. It is just to compute the digest. And so you can imagine that because of this chaining rule over here, so every bit of the message has something to do with the latest block. So this latest block is, we treat this one as the fingerprint of this entire computation, and that would be enough to represent that for this given key and the message, this would be the 128-bit, for example, fingerprint from this message, and that would be enough to treat it for hash function. So this would be the rough idea, but I mean, recently the problem is that the output number of the bits for this block ciphers are, for example, if you use AES, it is only 128 bits, and we know that 128 bits is not enough due to the birthday attack that we've discussed last week. So because of that reason, block cipher max are not quite popular because, at the end of the day, we are limited to very few number of bits. And nowadays we require to use at least, 512 plus number of bits. So this is not an attractive design anymore, but just the possibility that, you could use this idea for the HashMac as well. All right, so so far we've been discussing about many different design of hash function, and just like block ciphers and symmetric key encryption systems, we also discuss that what is the ideal scenario. Remember for symmetric key cryptography, we discussed that for these functions to for every encryption to be ideal, then the key size is huge, so basically we cannot afford to use them. We show that we use a small subset of keys, so then we turn it into a practical one. And I think the same thing we've discussed about also ideal encryption system in terms of security, that I one time passed that scenario, but we said that it's hard to generate the key. So we've been keep talking about these ideal scenarios for every design, and today we get to discuss about so we know that we can design hash function from scratch. We know that we can use block ciphers to do it, but it's a good moment to think about it, that what would be an ideal design. So the ideal design of a hash function is going to be something like, it is really a random function. It's a mapping. It takes some pre-image and then it map it to some smaller domain. But what we want to be as a perfect thing is that this function itself has to be random. So ideally, the way that we want it to work is that, suppose that the output of the hash function is n bits. So what we want it to do is that every time that we pass a message to compute the hash of this message or input, so we want the f function to do one simple thing and toss a coin for n times, and then generate a quite random number for this message and map this, saying that, okay, the hash of this message is going to be this n bits. And then in order to define this, then we have to have a sort of lookup table. So let me give you a rough idea. So we are talking about a hash function that we need to have a table for storing its results. So the idea is that when you ask to compute the hash of M1, then this function would go, and we know that the output is n bits, so it would go and toss a coin for n time, and then we know that coin tosses are one of the best ways that we can show randomness. So after for every time, if it is a head, we are going to write 1. If it is tail, we are going to write 0, and and so on and so forth. So we continue this until we generate n bits, and that would be the hash value for that message. And then we continue with the same technique. So if somebody asks for some other message M2, then we are going to maybe compute totally different thing, so and so on and so forth. So we basically continue with this, and then the idea is that why do we have to have a table? So remember that if it is possible that somebody comes back and ask for the hash of M1 again, we cannot return any other random value, because we are saying that we are defining a specific hash function. A hash function itself, remember, it was not a randomized function. It is a deterministic function. Every time you ask for the hash of the same message, you should get the same output. So that is the reason that we have to set up this table. And every time that somebody asks for a message, we toss coins, and then we generate a random value, and then we return it as a hash of that input, and then we just store it so that if somebody asks it again, we can return it. So imagine that here we could of course have a lot of repetitions over here, because we know that the domain is limited, only n bits, but the message input is huge. So there would be many different messages that somebody can submit to do the query. And at some point, we would start to see the repetitions. That is quite fine. Now that we know the definition of the hash function, we know that that is the case. So you might wonder that why do we do so? Why do we have to, toss coin? The reason for that is that just because of this equation over here. According to this design, with n bits, we would be able to generate values from 0 all the way to the 2 to the n, right? So then if you want to compute the probability of some hash of some message to be exactly x, to be exactly whatever over here, then that probability is going to be 1 over 2 to the n, right? Why we can say so, why we can claim so? Because now every element, because we are generating these elements randomly, we have a uniform distribution. And every entry, every output of the hash function has the same probability to appear as anyone else, because of our design that we use the coin to generate the output. And because of that, we get this nice property that probability for if you want to guess the hash of some message, your guess is going to be just 1 over all possible elements that we can get on the output. So that would be quite natural. This would be the ideal hash function, because in the proofs we can use this probability to accomplish a lot of good stuff when we are trying to prove the security of any crypto system that uses the hash function. But unfortunately, we know that in practice we are using practical hash functions. We didn't see any hash function we discussed so far that it uses this sort of lookup hash table. So that means that, what does that mean? So it means that we cannot guarantee this probability for every element, and there are some elements, because of the design of the hash function, we can't even find them, but they could be there, that some elements, they have higher probability, meaning that, for example, this whatever particular value that we have over here, a lot of m's that we query, their hash result would be this value. We don't know why, just because of the design of the hash function, perhaps. And those hash functions are, remember that they are safe. We don't know how to prove that, we cannot find collusions in those hash functions. But we know that there must be some values on the output that they are very highly probable than the other ones, and many messages would map to those values. And if that ever occur, then when we are proving for the proof of security, we don't have this nice notation, so nothing is uniformly random. And that would bring some challenges in the practice for proving the security of some crypto systems. So because of that, we are generating this so-called ideal hash functions, because with the ideal hash functions, we are designing it in such a way that we can guarantee this probability over here. And so we are going to utilize this to prove different crypto systems not being worried about, the defects or the weaknesses of the hash function. So we are going to stick to ideal hash function. But I think now you know that in practice, the difference with practical hash functions is that in practical hash functions, it's not guaranteed that the probability of the outputs are uniform, right? So in short, that is the only difference that you want to remember. So now that we know that, I think we are getting close to what is so-called a random oracle model, and we are getting very ready to start to prove the very first crypto system together. So now that we know about the ideal hash functions, now there is a very correlation between that and a random oracle model. So in the ideal world, we say that the perfect hash function is so-called a random oracle. So you remember the random oracle was an object that could do powerful things in a constant time. So ideally, we want the output of the hash function to be random, and also its output to be uniform. And it looked like that the ideal hash function that we designed in the previous page would pretty much pass this definition. It is a random function, and then so the way that it works is that from now on you will see that we have some adversary called f, and then we have some oracle. Let me put oracle over here. I think it would be better. We have some oracle of the hash function that we call it O of H, means the oracle of the hash. And then we have some attacker over here. So attacker would send a message to oracle, say that, hey, what is the hash of this M1? So we know that oracle in the background, he will go and generate the table, and then he would toss a coin for n times, and then he will compute the hash of M1. And then he would return and saying that, you know what, this is the output for this M1, right? And then so the adversary over here would basically send a query for another one. So he asked for M2, and then we would toss the coin again, and we send the hash of M2. And then with the knowledge that if at some point he asks for, he goes ahead and then he asks for M1 again, then we know that we shouldn't toss those coins because we already have the hash. We've already computed the hash of M1. We have it in our table, so we would just basically return the edge of M1 again, right? We already have it in our table, so the results are consistent. So this would be, last time we talked about oracles, and then so this is the very easy way to instantiate this oracle. So you see that now we have this, we require to have a random oracle hash function, and then now we know, we have an idea how to instantiate this. So there is an interaction. So you can imagine that you write a class in your, you're writing a code. So you call a different class for computing a hash function, right? And that other class is a random oracle O of H. And then in the construction of that, this other class that provide you a hash function, he has a database. Then every time you query some message, he does the random coining, toss the coin or generate a random number, and then store it in the in the database, and then returns that random number for you as the output of the hash function, and so on and so forth. So this interaction, that's what I want to say, is that it looked like a function call that you normally do when you write a code. So it doesn't have to be an object that resides outside of your computer. It could be also instantiated on the network, And then imagine that you have a web service for this, server that instantiate this random oracle hash function. And then every time that you want to compute the hash of some message, you basically communicate with this oracle through the web service. You call the function from the web service, you pass your message, and then it does the same thing on that server, have a database, store the values that it computed, and return the results to you. So could be both of them. But so now I give you the rough idea that these things can be implemented in the practice. It is just, we call it random oracle or just oracle because these are not efficient to be used in practice. That is the only problem. In practice, you don't want to maintain this table, or if two users computing this hash function, then they would have different values for every message. And if they want to communicate with each other and run a protocol, then the result of the very same hash function that they try to communicate with wouldn't match. But that wouldn't work in the protocol things. But only for these ideas that we want to prove, it would be a very good thing to stick to. Right. So that being said, let's address the elephant in the room. Today we want to discuss about this signature with hash function. I think we've seen this before. So it is a RSA RSA signature scheme, and then we are going to prove it today in a random oracle model under RSA assumption. So let's just start from the beginning. There are words and text here that we want to discuss before we get to the proof. So the first thing first, you see the big thing that it says full domain hash RSA signature. So the very first thing you want to ask yourself is that, what does that full domain hash function means? So remember that when we are working in RSA, so we are working on some Zn, right? And then n is a huge integer where n was equal to p times q, right? So sometimes you say that n is the length of the bn is roughly 1024 bits, right? So it's a very basic one. So that's what we know. So we are dealing with some messages that are, we are in an RSA crypto system. The group that we are working on is would take up to 1024 bits. Okay. So that being said, we know that the hash functions are the output of the hash functions are usually 128 bits, 160 bits, 200 bits, 512 bits. But the problem is that if we use them for hash function, it only covers a very small set of numbers in Zn. So when we are talking about the full domain hash function, it means that is a hash function that the output of the hash function is maybe 1024 bit. It covers the entire set of elements in the Zn. That's what we are talking about, right? So it covers the output. You see that it is a little bit different hash function. In practice, maybe it would be hard to find such a hash function, but well, now we are in the theory, so we can wish for whatever we want to have. So one of the idea is that you see that when you sign, you compute the hash of every message. So the idea is that if this hash function is not a full domain, then it only covers a very small portion of the all element that we have in Zn. And when you do that, then somebody can say that, what, the only advantage of the RSA is that this group is huge, but when you restrict it to a very small portion, imagine this is entire Zn, and then your hash function is the number of the bits are very small, and then you cover only this area, right? So if that is the case, then somebody can say that, oh, well, I can go pre-compute a lot of things, and maybe I can use my pre-computation idea to see if I can recover any message, right? So to eliminate that and make it easier at the end for us to compute the success probability of the attacker, we just wish that we have a hash function that doesn't cover this small area. It covers the entire elements in the ZN. So that being said, the signature scheme is pretty much the same. Every time that somebody wants to sign a message, all you do is to use this full domain hash function, compute the hash of the message, raise it to the power t mod n, that is going to be the signature. In order to verify this, so verification algorithm takes a message and a signature, right? And then what we would do is that we get the signature, we raise it to the power e, right? E is a public key of this user, so everybody knows e. So what would be the result? This would become the hash, sigma itself is a hash of m to the power d, and then we raise it to the power e. So this is going to be a hash of m to the power de, and this is just going to be hash of m mod n. Okay, so this is step 1, and then in the step 2 we are going to compute the hash of m itself, so hash of m, right? And then once we have done so, we are going to check if this if 1, the result of 1 equals to result of 2 or not, right? If we directly compute the hash function, we know what hash function this user uses. We compute the hash function, and also we raise this sigma to the power e, and then we know that that would spit out the also a hash function. If these two results are the same, it means that nobody has changed the message along the way. So that's how we verify it. So remember that we raise this one to the power e, and it has to be equal to the hash of m. That's how we did verification on RSA signature. So today what we are going to do is to prove that this design is secure in a random oracle model under RSA assumption. So what was the RSA assumption? So I think this is a typo over here. This should be X. So it is hard to compute the ETH root, right? So that means that given n, E, which is the public key, and this Y, Y is some X to the D mod n, it is hard to recover X given this information, right? So we know that this is the RSA assumption. We have two ways to do it. Either we factor the n, after factoring, we compute phi n, and then we can recover D, and then, that's how we can do this computation. Or if somebody give us the phi n, we can also go and directly compute, the D. But the point is, this signature problem that we want to solve is a little bit different, but they are correlated to each other. So let's just define it very precisely. In RSA problem, now we are given E, N, and Y, and then we are asked to compute X, which is the east root of Y, right? That's what we are asked to. In RSA, oops. Signing security problem. We are given, again, N and E, the public key, and then we are asked to return a forged signature. When we are proving the signature, we are trying to prove that nobody without the key can forge any message, can sign any message. But we are saying that if somebody can break this RSA signing security problem, it means that they can forge a signature without knowing the secret key. So return some M and sigma such that we make it very clear that sigma to the E should equal to the H of M mod N, right? So this way we make sure that the relationship between them should be correct. So the whole point of, they are a little bit correlated to each other. So that's what we are going to do today. So we are going to show that if somebody can break this, provide the forgery, then we can use this guy to solve this problem. So today, that's why they are a little bit different, but they are very correlated to each other. So today, we are going to show that computing the ETH root, that we define this one to be pi problem, we can reduce in polynomially time to another problem called gamma. This guy is full domain hash function RSA. So after we do this reduction, we are kind of correlating these two problems with each other. We are saying that if somebody find this forgery, can forge, can break this crypto system, we are designing a signature scheme, which means that if somebody don't have the private key, they shouldn't be able to, sign any message. But we are going to show that if somebody can sign a message without having the private key, and the signature has to be correct, has this condition, then we can use that guy, use this forged signature to solve this RSA problem. And therefore, these two problems are correlated to each other. So we have to twist this RSA problem. We cannot work directly on the RSA problem, hard assumption. So we twisted a little bit, and then this is the overall work that we are going to do today, showing that, if somebody break this, can forge and, forge a signature, then we can use that forgery to solve RSA problem, hard assumption. And therefore, we are going to assume and, find out that, okay, we know that RSA is a hard assumption, then nobody would be able to provide the forgery, because if somebody ever provide the forgery, we are showing that RSA problem is not a hard problem anymore, and we know that that is wrong, and therefore the forger should not exist, right? So that's how we show the security proof for this problem. Anyways, let's take a 10 minutes break, and then we come back at 9 o'clock to continue.